Howdy, I'm Dr. Kate Davis with the Electrical and Computer Engineering Department at Texas A&M, and I'm also the PI of the CYPRES project. So first, what is the problem? The problem is that the grid is a cyber-physical system that needs to be resilient against all kinds of threats. This means that the grid must be able to ride through and maintain its function, even in the presence of an intelligent adversary. So, how to ensure grid resilience while understanding, predicting, and preventing impact of cyber vulnerabilities is the challenge. The CYPRES team intends to create and use a cyber-physical mathematical model of the power system to provide stakeholders with actionable information to make decisions about the system. The title of the project is Deep Cyber-Physical Situational Awareness for Energy Systems, a secure foundation for next-generation energy management. For short, we call our project CYPRES, which stands for Cyber-Physical Resilient Energy Systems, since resilience of the power system and energy delivery systems is the ultimate goal. The goal of the CYPRES project is to envision and design a next-generation energy management system that is truly cyber-physical. So in CYPRES, we model the power system together with the cyber system and collect alerts and data from both of these. And we create an analytical cyber-physical model with which we want to perform several things. First, we want to do cyber-physical state estimation. This is, we want to have an idea of where it is that we are in the model. And we want to prioritize risks based on access paths, vulnerability, and impact to the system. And we want to provide situational awareness. Basically, this means we want to be able to provide decision support and recommendations to stakeholders. And from these, we want to recommend control actions and countermeasures using both available cyber and physical controls and taking into account where we are in the system. Our team has created a large-scale cyber-physical power system model that is implemented in our testbed, which we also created, along with a new modeling and analysis software application that will provide the platform for CYPRES. And here we would like to demonstrate just one incident scenario with this model. Performing this demonstration for us, we have three amazing CYPRES PhD students, Abhishek, Sahu, Hao Huang, and Dave Mao.
This is Hao. As Professor Davis mentioned, we are showing a scenario of cyber adversary in power systems. In power systems, there are various communication protocols for communications between devices and control center, such as IEC 6180, Modbus, DMP3, etc. In our demo, we consider DMP3 as the communication protocol, and the cyber incident will target the DMP3 communication and modified payloads. DMP3 has master and outstation for data measurement and control. In the field, all devices, such as relays, act as DMP3 outstations, and control center is the DMP3 master. In our demo, the cyber adversary will poison the communication network, target to impersonate the DMP3 master, and drop or modify the payload. Then, the substation will receive untrusted control command and will show unexpected behaviors. Without prevention or immediate relief response, it may induce severe contingencies and causes cascading failure in the network. Here is the overview of our scenario implementation. In this slide, we are showing the most severe impact of the cyber incident, as we mentioned. The cyber adversary will find the entry point from the communication network and then go to the utility DMZ, the control network, and then go to the substation network and find the substation they try to impersonate. Once they make it, they will modify the payload, which will change the device's status and change the topology of the network. If there is no prevention or relief response, there will be overflow in the network, which can cause a cascading failure, and then the whole system will go to the blackouts. Next, my colleague Abhijit will show the detailed steps of the cyber adversaries.
Hari, this is Abhijit. The primary goal of the CYPRES project is to perform a multi-stage attacks and to devise a mechanism to prevent or detect intrusions at early stages of those attacks. Hence, in our testbed, we'll be performing multi-stage attack as the final iteration of our demo. The attacker in its initial stages will try to find its target, which is the most vulnerable in the utility network. It's the employees who would open some spear phishing mails that will give access for the intruder to get into the business network. Once they are into the business network, they would compromise the firewall separating the business network from the DMZ and get into the DMZ network. Once they are in the DMZ network, they exploit the vulnerability in the web servers, database server, and proxy server in the DMZ network to get access to the data that are stored in the database server of the utility control network. There, they exploit a few other vulnerability and create a botnet by which they can remotely access the bots installed inside the DMZ network. Those bots would allow to compromise the firewall that separates the DMZ from the utility control network, and the attacker can gain access into the utility control network. In this utility control network, there is a DNP3 master which would be probing measurement from the substation devices and sending some control command to the substation devices. So the attacker would impersonate the DNP3 master by performing an ARP-cast poisoning attack on the network switch inside the utility control network. So the DNP3 master, which is impersonated, would get access to send some malicious modification DNP3 command, and they can create contingency, as my friend Hao mentioned. In our demonstration, we are considering the Sanjuan substation for performing an attack. As you can see, there are two layers in DNP3 in a real world where the DNP3 master from the utility control network is connecting with the DNP3 outstation in the substation, and inside the substation there is a DNP3 master communicating with the real DNP3 field devices, which is acting as an outstation. So there are two hierarchy of DNP3, but for the simplification purpose, we are considering only one layer where the utility control network is acting as a master and the DNP3 outstation is acting as the field devices, which is simulated using PowerWall DS. A DS is a platform to perform real-time simulation of power system.
As mentioned, the adversary is in Sanjuan substation, which locates the south area of the Texas. From the data, we can see there are 9 branches connecting to the substation. For the adversary, the most severe situation it can create is to open all devices, and it will directly cause overflow in the system. If there's no intervention on the protective relays, then they will trip all those overflow branches, and it will cause instability in dynamics as shown there. If there is no further operation of load shedding or generation adjustment, etc., then the scenario will evolve into a cascading failure and ultimately become a blackout. Now, my friend Abhijit will go through all the steps.
The implementation of our testbed comprises of 4 virtual machines running in our servers for the CYPRES project. In first virtual machine, we'll be emulating the DNP3 master, which is a Linux machine where we run the DNP3 client and we get the console to write DNP3 commands. The second application is the centralized application, where we demonstrate the synthetic communication model that we created for Texas 2000 case, where we have 150 utilities talking with the balancing authority and the backup balancing authority, and each of these utility control center talking with the substation devices, which are a substation control network. There are like 1250 out of them in this model. And this centralized application would provide situational awareness and get real-time traffic alerts generated in the communication network so the operator can take some optimal response. We develop our data fusion engine in this application and demonstrate for the operator as well. The third VM, we are emulating the communication network. The core is a emulating environment that provides us the platform to emulate the utility control network, which is bridging to the DNP3 master at one end, and there is a substation control network bridging to the DNP3 outstation, which is the field devices emulated or simulated, you can say, in the Power DS, which is acting as a real-time server for running the power system cases. This core emulator would be used to perform cyber intrusion in our case. As mentioned in the presentation, we are having 4 VMs running, and the first VM would be...
So we have a DNP3 master here, and now I start the DNP3 master.
The DNP3 master would be triggered by our front-end application to get a console to write the control commands that we can see in the DNP3 outstation.
In this case, substation Sanjun is already open, and we are trying to close through the DNP3 master.
All the branches are open. So once the application communication between the DNP3 master and the DNP3 outstation is through this core network. If you open the TCP dump, then we can start our DNP3 master. Once we start the DNP3 master, we get a console in the client application.
So as you can see, we have a lot of functions that can use in this DNP3 master client. For example, like direct operate or the select and operate. Right now, I will close a circuit breaker by using this DNP3 master. So in the Power DS, when we check the logs of the actions, we will see this branch is closed through the DNP3 NAS client.
We will try to give another command to close as well.
So as you can see, we close another circuit breaker.
Yes, and we can check the status over here, the command that was sent, it was successful, and it can be broadcasted here to the application. Now this view shows the control network where there are like 150 utilities, and there is a balancing authority and the backup balancing authority. We could go into one of the utility control center. So you see there is all the list of substation network connected to this utility. This is the firewall interfacing with the substation. This is the firewall, and this is the DMZ network, which is source of intrusion in our case. And this server over here, it is acting as the DNP3 master, which is emulated using another VM. So if you go to the DNP3, the San Juan substation, we can see the list of load relays, distance relays, and overcurrent relays located in this San Juan substation. We can currently get the alerts from the router located in the core network. Here is the router in the San Juan control center, and we can get logs from that code. So now the operation is normal and functional, and the alert doesn't make much sense, but we will get more alerts when there is an attack. Now my friend Patrick would go through the attack scenario, because we talked this machine which is inside the utility control center would be emulating or impersonating the DNP3 master and do the ARP cache poisoning attack on this switch.
So on the core network emulator, we first open up an SSH tunnel into this control PC. This tunnel is a network not connected to the simulation, so it won't affect anything else. So you can see it's control PC 1. PC 1. And we have a script that we can run. It's a Python script that will first do the ARP cache poisoning along this switch to redirect the traffic. And let me run that. And as you can see, it started the cache poisoning. Now it's just redirecting the DMP3 packets, capturing them, and replaying them.
So we can try to write another DNP3 command and see whether that command is going through or not. So we get an undefined status because the DNP3 payload format has been changed and it is unable to recognize the DNP3 response coming up from the outstation. So that's how we perform a cyber attack, and we can see it in our application. Yeah, the close command is not executed because the attacker intruded into the utility control network. So our application, we will be improving it to observe real-time traffic coming from the cyber side as well as the physical side, and we can find what are the responses operator should take based on those alerts and making correlation among them, as well as we can run some attack tree view to observe the list of vulnerable. So these are the list of the host, and these are the attack paths that an intruder took into compromising the substation network, and we will improve on this because this is just showing some static paths.
So the next steps on CYPRES are to continue closing the loop with the unified model. This demonstration focused a lot on the model and representing, managing, and visualizing this cyber physical model and showing how we can fuse streaming inputs from the power system side and the cyber communication side together into CYPRES and our evaluation platform in our testbed. The next demo of CYPRES will focus on early attack detection with this model and data.